Here's a rigid body kinematics question that we can actually solve using Euler's formulas. And if we do that, you'll see that the fact that we're using vectors and the Euler's formulas themselves will take care of all the signs and all the directions of the vectors and so on. So it's going to show that Euler's formulas will be a very rigorous way of tackling any similar problems. And if you wish to see anything like this in the future, or if you have any suggestions for any topic or any specific problem, maths or physics related, let me know in the comment. So here's what we're dealing with. We have a collar which is attached to point A, and that collar is traveling downwards with a velocity VA. And what we're asked to find is the angular acceleration of this other link here, which is called OB. And link OB and the collar are attached via another link, which is AB. Okay, so let's try to see how we can actually do this. First of all, if we're using Euler's formulas, we have to define our coordinate system. So I will place a coordinate system x and y, which is attached to point A, and it's moving together with the AB link. And we can write down that VA, the vector VA, the velocity of A, is going to be equal to minus VA, that's the value, times J. Okay, and the minus tells us that VA is acting downwards. So using this, we can try to get an expression for the velocity at point B, right? So the velocity at point B, given our Euler formulas, is equal to VA plus the angular velocity of link AB, and then cross product with AB. That's the position vector of B with respect to A, of course. So let's see what we have. We have that VB. Now, VB is the velocity of point B, obviously, and B is attached to O. So, well, B is attached to the OB link, and because O is hinged, not fixed, but hinged, the velocity of B is purely in the x direction, right? You cannot have the velocity of B being anything like this because it would have a component that goes upwards and the link is solid, so this simply cannot happen, right? So the velocity of B is purely in the x direction. So I'll write VB as VB times I. I don't know if it's positive or negative, but we'll find that out soon. So that is VA, which we know is minus VA times J plus, and then in terms of the second term, we have the determinant that we have to deal with, which is omega AB, and then AB is just L, right? Because the position vector of B only has an x component, which is given by the distance L. So VB times I is therefore equal to minus VA times J plus, and this determinant only has the J component associated with it, which is omega AB L. Right, so here's something interesting that happens. On the left-hand side, we have an x component, right? We only have a vector, we only have the unit vector I multiplied by VB, and on the right we have the j component. But the two have to be equal to each other, and you cannot have the I component be equal to the j component unless both of them are 0, okay? Because, well, another way to think about it is if on the right you have an I times 0, then this has to be equal to this, which is basically the same thing. So on one hand, we get that the velocity of B is equal to 0, and we also have that the j component on the right is equal to 0, which is minus VA and then plus omega ABL. Omega ABL is equal to 0. which ultimately tells us that omega AB is equal to VA divided by L. Now, why is this the case, though? Why is VB equal to 0? So this is telling us that while the AB link is purely horizontal, the velocity at B is null, right? And in a way that makes sense, because if you think about it, I'll erase this for a second. So B can only move to the left or to the right. So B can only move in the x direction as long as OB is purely vertical, right? But in this moment, this end A of the link is purely moving downward. So this point here does not have any horizontal component of the velocity. And if this end doesn't have a horizontal component, then this end at B must not have a horizontal component either. Because let's say if VB was like this, and if the velocity of A is 0 horizontally, it means that the link would compress, right? Alternatively, if the velocity of B was that way, and there's no horizontal component at A, then the link would get longer, which doesn't really make sense, right? So the fact that we got VB equals to 0 makes all the sense in the world, right? And the other thing we got was that the omega of AB is VA over L. Now, another thing which comes up as consequence of VB equals to 0 is the fact that the angular velocity of OB is also equal to 0. So that's the angular velocity of this link right here, right? I'll call this omega OB. So because clearly VB is the length of OB times omega OB. And if this is 0, then clearly this is 0. Or if this is 0, then this is 0. So omega OB is identically 0. Okay, so now that we found this, let's try to maybe find an expression for the acceleration of point B. And we're going to do this in two different ways. So first of all, I'll say that the acceleration of B equals, and then I will place my coordinate system here again, like that. And we have that the acceleration of B is equal to the acceleration of A, and then plus we have alpha cross the position vector of B, which is AB, and then minus omega squared AB times AB. So this is just Euler's equation for acceleration. Now, there are a few things here to note. First of all, we don't know what this is. And secondly, we have the fact that this is equal to 0. So here's what we can then write. We can write that AB, the acceleration of B, is equal to the determinant. So this is ijk, and that is 0, 0, and this is alpha AB. That's strictly the angular acceleration of the AB link, and this is just L because it only has an x component, minus, and this here is what we just found. So omega squared AB is VA squared by L squared times, and then AB is L times I. Okay. So what we can then do is we can find what is the acceleration of B, obviously. So first of all, we solve the determinant, and we see it only has a j component, which is alpha AB times L. And the rest of it is just minus VA squared over L multiplied by I. Okay, so this is the acceleration of B. Now, it doesn't really help us. This expression by itself doesn't really help us that much because we don't know what this is, what this alpha AB is. So we have to do something more. And the other thing we'll do is we will find an expression for the acceleration of b, but this time we're going to do it from here. So I'm going to put my coordinate system into point O, and this coordinate system is fixed to link OB, and using that, we are going to find the acceleration of B from a different direction. We're going to find the acceleration of B with respect to point O. So the acceleration of B is the acceleration of O plus, and now it's just the same formula as previously, it's alpha OB cross OB, and then minus omega squared OB times OB. Right, the first thing to note is this is 0 because the point O is not going anywhere, and this is also 0, right? This is what we got at this point, which means that the acceleration of B as measured from point O only depends on this cross product, which is I, J, and K, and then we have 0, 0, and then alpha OB, and then OB is minus R, right? The length of the link is R, and B is below O, so that's in the negative y direction, so that would be minus R and 0. So that is I multiplied by alpha OB times R. Okay, right, so we have the acceleration of B expressed like this, and the acceleration of B expressed like this. But those two accelerations have to be exactly the same, which means that this here, the I component of acceleration of B, has to be equal to the I component of the acceleration of B, which means that the alpha, the angular acceleration of the vertical link OB times R, is equal to minus VA squared over L, which finally tells us that alpha OB is minus VA squared over RL. And that's exactly what we have to show. And of course, this minus sign here tells you that the angular acceleration is going to be clockwise, right? And it makes sense if you think about it, because as point A will start going down, so point A has a downward velocity, then this link, this AB link, is going to start dragging the OB link in a clockwise direction. So it will accelerate OB clockwise, and this is why we have this minus sign here in front of the angular acceleration. And that's the end of the question.